Food, the heartbeat of our existence. It's essential for our survival and vital for our health and growth. Access to nutritious food is a basic human right and a cornerstone of healthy communities. By ensuring food security and improving nutrition, we can create a better world where everyone has the opportunity to live a healthy and fulfilling life. The Sustainable Development Goals, SDGs, also known as the Global Goals, were adopted by the United Nations in 2015 as a universal call to action to end poverty, protect the planet, and ensure that by 2030 all people enjoy peace and prosperity. The 17 SDGs are integrated. They recognize that action in one area will affect outcomes in others, and that development must balance social, economic, and environmental sustainability. Every year, the UN Secretary-General presents an annual progress report based on the Global Indicator Framework and data produced by national statistical systems and information collected at the regional level. One of the goals is zero hunger. Pledges to end hunger, achieve food security, improve nutrition, and promote sustainable agriculture. It aims to end all forms of hunger and malnutrition by 2030, making sure all people, especially children, have sufficient and nutritious food all year. This involves promoting sustainable agriculture, supporting small-scale farmers and equal access to land, technology, and markets. The world is right now facing the worst global food crisis in decades. The combined impact of conflict, climate change, COVID, and the cost of inflating food prices due to the conflict and war crisis. Every day, too many men and women across the globe struggle to feed their children a nutritious meal. In a world where we produce enough food to feed everyone, 821 million people, 1 in 9, still go to bed on an empty stomach each night. Even more, 1 in 3, suffer from some form of malnutrition. Undernutrition, at its core, is a dietary deficiency that results in poor health conditions. Here, we break down 5 major factors that contribute to undernutrition in children. 1. Poor quality of diet. Undernutrition happens when a poor diet lacks essential nutrients needed for good health. This can lead to problems like stunted growth and a weak immune system. 2. Poor maternal health. Mothers who are malnourished during their pregnancy can experience complications giving birth. Many children are born small because their mothers are undernourished. Severely undernourished mothers can also have trouble breastfeeding their infants. 3. Socioeconomic status. Poverty is the #1 cause of undernutrition in developing countries. Oftentimes, families living in poverty lack access to fresh fruits and vegetables. At least 240 million children live in countries affected by conflict and fragility. These children are at heightened risk of death before age 5, stunted growth due to undernutrition. 4. Climate change. Currently, climate change is contributing to the degradation of precious resources, as severe weather events, like droughts, become more common and affect harvests, leading to less food for human consumption. 5. A war and conflict. Hunger is also a product of war and conflict. During periods of unrest, a country's economy and infrastructure can become severely damaged. This negatively affects civilian access to food by either driving up food prices, interfering with food production, or forcing people from their homes. Without enough nutritious food to eat or the ability to absorb the right nutrients, children under 5 are at high risk of acute undernutrition, which can lead to death, or if a child survives, can cause stunting or wasting. The indicators stunting and wasting children under 5 years old will be used to measure the undernutrition of children in the continent. Stunting. Children who suffer from growth retardation, which means they have low height for age and will look short for their age. Children are considered as stunted if their height for age is below -2 standard deviations of the WHO Child Growth Standards median. Those below -3 standard deviations are considered as severely stunted. Wasting. Wasting in children is a symptom of acute undernutrition, which is a low weight for height. Wasting impairs the functioning of the immune system, and they will appear thin. Children are wasted if their weight for height, or BMI for age, is below -2 standard deviations of the WHO Child Growth Standards median. Those below -3 standard deviations are considered as severely wasted. For this project, we will focus on 2 regions that have the highest number of malnutrition children in the world, which are African and Asia. For the datasets, we have selected 5 countries with the highest rate of undernutrition children from each continent to analyze and interpret the data to see the pattern and study the correlation analysis. For African countries, we have selected Afghanistan, South Sudan, Chad, Burundi, and Nigeria. For Asia countries, we have selected Yemen, India, Pakistan, Indonesia, and Bangladesh. Data was extracted from the UNICEF website involving undernutrition children aged 1 to 5 years conducted for the period 2011 to 2016. Objective 1. To analyze the patterns of stunting and wasting children aged below 5 years old in Africa and Asia continents. Objective 2. To identify the likelihood of malnutrition children having both stunted and wasted in the continents. Objective number 3 is to predict the correlation between a country's GDP per capita and the prevalence of underweight children in the continent. Objective 4. Mothers aged under 19 years at their first childbirth lower chance the child to be underweight. Wasting and stunting are critical public health issues affecting children globally, particularly in low and middle-income countries. Wasting and stunting remain pervasive challenges among children in African and Asian countries, where socioeconomic disparities and food insecurity are prevalent. Contributing factors include inadequate maternal nutrition, suboptimal infant and young child feeding practices, recurrent infections, and limited access to healthcare and sanitation. In 2011, global patterns of stunting among children under 5 revealed significant disparities across regions and countries. Sub-Saharan Africa and South Asia were particularly affected. In these regions, chronic malnutrition contributed to a large proportion of children being too short for their age, hindering physical and cognitive development. Conversely, regions with better socioeconomic conditions and robust healthcare systems generally reported lower rates of stunting. From this study, we have collected data from 2 continents that contribute to the higher rate of stunting and wasting children from 2011 to 2016. We have chosen the top 5 of countries from each continent to do the analysis. Here are the percentage of stunting and wasting children in Africa and Asia. From the Africa continent, we can see that Burundi have the highest rate, while Indonesia is the most country that contribute to the highest rate of stunting and wasting children. The table provides descriptive statistics for 2 variables, the percentage of wasting children and the percentage of stunting children. The percentage of wasting children, the mean value is 3.8801, indicating that on average, 3.88% of children are affected by wasting in the observed population. The median value is 4.0400, reflecting a relatively symmetric distribution. The standard deviation of 1.7627, implying a moderate level of variability or dispersion in the data. For the stunting data, the mean value is 44.1678, indicating that on average, 44.17% of children are affected by stunting in the observed population. The median value is 42.5846, which may indicate a skewed distribution towards higher values. The standard deviation is 8.8741, reflects significant variability in the data, meaning that the dispersion in the stunting rates across the observations. The histogram of the percentage of stunted children shows a non-normal distribution because it exhibits bimodality with two distinct peaks, one around 40% and another smaller peak around 60%, indicating the presence of multiple subpopulations or factors influencing stunting rates. Additionally, there is a slight right skewness, as the tail extends more towards higher percentages, and the distribution has a sharp peak around 40%. The histogram for the percentage of wasting children shows the distribution of values across the observed population. The mean percentage of wasting children is approximately 3.88%, with a standard deviation of about 1.76. The data appears to be roughly normally distributed, as indicated by the bell curve overlaid on the histogram. Most values cluster around the mean, with fewer observations at the extremes. This suggests that the percentage of wasting children is relatively consistent, with most areas having a similar rate of wasting, and fewer areas having very low or very high percentages. In the above data, Region 1 refers to Asia and Region 2 refers to Africa countries. According to the data, the proportion of wasted children is 4.7102 and stunted children is 46.6310 in Asia. While in Africa, the proportion of wasted child is a bit lower, which is the mean is 3.0500 and stunted children is 41.7045. This indicates that each region faces different nutritional challenges or takes different interventions. We can see that the Asia ranks higher on average in the percentages of wasting and stunting compared to Africa. Next, we will run a non-parametric test by using Mann-Whitney U-test. This test is to compare two sample means whether they are equal or not. The Mann-Whitney U-test results indicate significant differences between the distributions of these variables in the two regions. Asia has higher mean ranks for both wasting and stunting percentages compared to Africa. These findings, supported by both descriptive statistics and test results, highlight potential disparities in nutritional status between the two regions. From this analysis, we can conclude that stunting and wasting are two different health problems that affect children. When we look at the numbers for how many children are stunted versus how many are wasted, we notice that the mean and median of the percentage of stunted children are higher than those for wasted children. This tells that stunting is a more common problem in the group of children we studied. Standard deviation and variance are both measures of how much the numbers differ from the average. If these numbers are high for stunting, it means that the percentage of stunted children varies a lot from one group to another. This tells us that there is a greater difference in stunting rates among the groups we studied. Objective 2. To identify the likelihood of malnutrition children having both stunted and wasted in the continents. Children experiencing both stunting and wasting simultaneously face a severe double burden of malnutrition that heightens their vulnerability to long-term health complications and developmental setbacks. The connection between stunting and wasting often manifests in contexts of severe malnutrition and poor overall health conditions. Children who experience stunting may also be at risk of wasting. The hypothesis H null points out that there are no significant differences in the percentage of wasting and stunting in children. Conversely, H alternative proposes that significant differences do exist between the percentages of wasting and stunting. By testing these hypotheses using appropriate statistical methods, we can uncover meaningful insights into the prevalence and distribution of malnutrition. First, we will analyze the data by using the scatter plot. This scatter plot shows the relationship between the percentage of wasted children and the percentage of stunted children, without showing a clear linear relationship between the two variables. Visually, there seems to be a slight positive trend that the higher the percentage of stunting, the higher the rate of wasting, but the relationship is not strong. The chart shows the Spearman correlation coefficient between the two features and their level of statistical significance, p-value. As can be seen from the table, the correlation coefficient between the percentage of wasted children and the percentage of stunted children is very low, 0.017, indicating a very weak positive correlation. At the same time, the p-value of the two correlation coefficients is 0.90, which is more than p-value 0.05, shows that there was no significant difference in the percentage of children having wasting and stunting. Overall, there was a very weak positive relationship between the percentage of wasted children and the percentage of stunted children. From the tests that have been done, we now can accept the H-null, which indicates that there are no significant differences in the percentage of wasting and stunting in children. This shows that if we were to randomly select groups of children from similar populations, the differences we observe in the rates of wasting, low weight for height, and stunting, low height for age, could likely occur just by chance, rather than due to any underlying factors or true differences between the two conditions. Objective number 3 is to predict the correlation between a country's GDP per capita and the prevalence of underweight children in the continent. Understanding the correlation between a country's GDP per capita and the prevalence of underweight children is crucial for several reasons. GDP per capita is a key indicator of a country's economic performance and overall wealth. In many developing or poor countries, low GDP per capita often reflects limited access to essential services such as healthcare, nutrition, and education. These limitations can lead to higher rates of underweight among children, as families may struggle to afford nutritious food and healthcare services necessary. By analyzing this correlation, we can better understand the socioeconomic factors contributing to child malnutrition and identify targeted interventions to address these issues. First thing, we need to do the descriptive statistics. Descriptive statistics provide a quick summary of the data, allowing us to understand the central tendency, mean and median, and dispersion, standard deviation, of the variables. The table shows average GDP per capita is about 1,338.8925, with high variability. In contrast, the average percentage of underweight children is about 33.778, with much less variability. This means GDP per capita varies widely, while the percentage of underweight children is more consistent across the regions. Next step is to do the scatter plot. Scatter plots help us to visually inspect the potential relationship between the variables. The scatter plot presented shows the relationship between GDP per capita on the x-axis and the percentage of underweight children on the y-axis across different countries over the years. This analysis aims to interpret the pattern, identify the correlation, and provide insights. From our observation, we can see that the scatter plot does not show a clear linear trend. Instead, there seems to be a more complex, possibly non-linear relationship. There are clusters of data points indicating higher concentrations of underweight children at lower GDP per capita levels. As GDP per capita increases, the percentage of underweight children generally decreases, but there are significant variations and outliers. Since the data in the scatter plot is not normally distributed, we choose Spearman correlation coefficient. The correlation coefficient between the percentage of underweight children and GDP per capita was 0.119, indicating a very weak positive linear relationship between the two variables. A p-value of 0.367 indicates that this weak correlation is not statistically significant. In the context of this analysis, there is a slight tendency for countries with higher GDP per capita to have a slightly higher percentage of underweight children. However, this correlation is not strong enough. The R-square value of 0.000 in the model summary indicates that GDP per capita explains 0% of the variation in the percentage of underweight children. In the ANOVA table, the p-value is 0.878, which is much larger than 0.05. This shows that the regression model is not statistically significant, providing insufficient evidence that GDP per capita is an important predictor of the percentage of underweight children. Based on these regression results, we conclude that GDP per capita does not significantly impact the percentage of underweight children in this dataset. Other factors may play a more important role, and further research is necessary to identify these factors. Objective 4. Mothers aged under 19 years at their first childbirth will not have a chance the child to be underweight. Current study found that children of young mothers, age below 19 years, more likely to be underweight than children with older mothers. Young maternal age at first birth is a significant factor contributing to child undernutrition globally because they often face physical and emotional challenges that impede their ability to provide optimal care and nutrition for their children. These young mothers are more likely to experience complications during pregnancy and childbirth, which can result in low birth weight and other health issues for the infant. This hypothesis testing process will help determine if there is a statistically significant difference in the likelihood of having underweight children between mothers aged under 19 years and those aged 19 years and older. The hypothesis null is mothers aged under 19 years at their first childbirth have a higher chance to have an underweight children. Hypothesis alternative would be mothers aged more than 19 years at their first childbirth have a higher chance to have an underweight children. This analysis will provide insights into the impact of maternal age on child health outcomes and guide policy and intervention strategies accordingly. The first is descriptive statistical and normality tests for two variables: the average age of women giving birth for the first time and the percentage of underweight children. According to the chart above, the average age of a woman's first child is 19.81 years. The overall distribution is slightly negative, -0.143, and the low peak state is -1.246. The average percentage of underweight children was about 33.78%. The overall distribution is slightly positive, 0.307, and the low peak is -1.152, which means that both variables are slightly flatter than the normal distribution. In the normality test table above, the Kolmogorov test show that the p-values of the two variables are 0.001 and 0.005 respectively. Both p-values are smaller than 0.05, so it shows that the data are not normally distributed. Based on the chi-square test results, p-value is bigger than 0.05, thus we accept the H-null. This will indicate that mother aged under 19 years at their first childbirth will have a higher chance to have an underweight children. Over a quarter of the world's under 5s, 161 million were stunted, with highest prevalences in Asia, 56%, and Africa, 36%. It might be surprising to learn that child malnutrition rates in Asia are higher than in Africa, especially since African countries are often associated with severe malnutrition. This must be due to media coverage of famines and humanitarian crises. However, several factors also contribute to the higher malnutrition rates in Asia. One of the factors is because the population density and size. Asia has a much larger population than Africa. Countries like India and Bangladesh have very high population densities, which can exacerbate issues related to food security and access to nutrition. The sheer number of children in these countries means that even a lower percentage of malnutrition can translate to a higher absolute number of malnourished children. We did an analysis on factors that can contribute to the higher number of malnutrition children, which are the GDP per capita for each country and the mother's age when they have their first baby. First, we found a weak association between economic growth and child undernutrition, which contrasts with the expectations. Countries with higher GDP per capita tend to have lower rates of child malnutrition. There are several potential reasons why economic growth does not automatically reduce child undernutrition. It could be the income growth not unequally distributed or does not necessarily investments that help improve children's nutritional status. Second, the experts say those born to younger mothers ages 20 to 24 were at a greater risk of diseases than those born to women ages 25 to 34. The biggest factors that the research linked to the eventual health of children were the mother's education level and the number of years she lived after giving birth to them. This analysis has shown that mothers aged under 19 years at their first childbirth will have a higher chance to have an underweight children. The young mothers may lack knowledge about proper nutrition and resources to support their child's health due to limited access to education and healthcare. Children born to young mothers might be at a higher risk of underweight. Socioeconomic factors like GDP per capita are more influential on child health outcomes than maternal age alone. The chi-square test results highlight the need to consider multiple factors, including economic indicators, to understand disparities in child health. Focusing only on maternal age oversimplifies the complex interplay of socioeconomic factors affecting child health outcomes. Undernutrition among children in Asia and Africa remains a critical public health issue, deeply influenced by a range of factors including socioeconomic status, food security, and access to healthcare. The persistence of undernutrition is linked to poverty, inadequate maternal nutrition, and limited access to clean water and sanitation. Comprehensive strategies that integrate economic development, improved healthcare services and education on nutrition are essential to combat this pervasive problem and ensure healthier futures for children in these regions.